Perfect. Well, thanks for the introduction. So I will present the work that we have been doing with Katalin Chilitscu, Ezekiel Vivas, and Antoine van Mulder, who are all present here in this room, about relational program logics and relational verification. So we already heard a bit about relational verification, but what is it exactly? So relational verification is the art of proving properties about two programs, here P and Q. And this kind of properties will bridge together the two programs. For example, we could prove program equivalence or refinements of the behaviors of one program with respect to the other, or also some kind of relative cost analysis when we have some cost semantics on the program. One particular case of relational properties is hyperproperties, which consider two different runs of the same program. So among important hyperproperties are non-interference or differential privacy. So there is a huge spectrum of relational properties that we might want to prove about programs. And in order to prove these properties, one of the most used tools for relational verification is relational Hall logics and its derivatives, such as relational separation logics. In relational Hall logics, we have two programs, P and Q, and we assert a relational specification by providing a precondition that must hold of the initial states of the two programs. So it's a relation between the initial states of the two programs, and a post relation that must hold of the final states of the two programs and potentially of their final values. How do we prove such triples that assert a relational specification about two programs? By using inference rules, such as this one, that ensure that sequence of programs are related whenever we can relate their subcomponents. We have this kind of relational program logics for many different kinds of effects. For example, simple relational Hall logic as presented by Benton can account for state and non-termination. And there have been a huge body of work about relational program logics for state and probabilities. But since we have so many different relational program logic, we would like to be able to understand what are the common features of all these relational program logics. And in order to do that, we'll take a uniform abstraction of effects, in this talk, monads, in order to distill the essence of relational program logics. And then once we encode our effects with monads, we want to understand what kind of structure it provides on the relational program logics. In particular, the algebraic notions that underlie the proof rules that we use in relational program logics. And then, once we have understood this structure, we want to be able to reconstruct relational program logics for a variety of monadic effects. So in this talk, I want to try to extract the unifying principles of relational program logics for arbitrary monadic effects. So how will we go to do that? Well, we'll use some previous work that we presented this year at ICFP in order to encapsulate monadic verification of monadic programs for unary programs. So we start from a computational monad, which encodes one of or many of the effects that you can see here, such as input-output or non-determinism or probabilities. And in order to talk about specification, we will also provide a monadic interface for specification. How do we do that? Well, actually, we can realize that pairs of pre- and post-condition put together have a monadic structure where the return operation corresponds to the specification you would give to returning a value, and where the bind operations allows to compose specifications for subcomputations. We can also do a similar thing for predicate transformer. For example, the continuation monad to proposition can be seen as a predicate transformer from postcondition on result value to precondition. And so, moreover, these monads have an order that corresponds to the entailment order on specifications, and so they are ordered. Then, once we have a computation monad that encapsulates effects and a specification monad which encapsulates specifications, we relate them by an effect observation, which provides the semantics of computations as specifications. Now, this thing works in the unary setting. If we want to go to the relational setting, we need to move from a situation where we have one computational monad, one specification monad, and an effect observation, to a situation where we can have two computational monads, one for each program. And these two programs need not to be the same, and they need not to resulting in values at the same type. So we need to account for all these differences. However, on the other side, the relational specification is only one. There is only one relational specification bridging the gap between the two programs. And so we'll need to explain what kind of monad-like object we need in order to account for this thing. But first, I would like to explain how we can reconstruct relational program logics out of such a setting where I have two monads, an object of relational specification, and a way to explain my computations as relational specifications. And in order to do that, I will introduce a relational judgment that takes two programs, C1 and C2, each program in its respective monad, and a specification W, where W can be, for example, pairs of pre and post condition. So with respect to standard relational Hoare logic, I'm putting together the two parts of the specification. So the W can really hold both the precondition and the postcondition. And then I will provide a semantic for this judgment by saying that such a judgment is valid whenever the specification, the relational specification that I compute for my two programs, C1 and C2, entails the specification W, where this entailment relation is provided by my object of relational specification. Then I will reconstruct rules of my relational program logic, organizing them with respect to their behavior with respect to effects. So I will have logical rules that are totally independent of the underlying effects, what I call generic monadic rules that talk about effects, but about the monadic interface of effect, and effect-specific rules that will actually poke at the actual content of my computational monad and the way I interpret them to be validated. So the first two parts are fully generics. The last one really depends on the specific effects that I have at hand and what I want to say about them. So let's have a look at generic monadic rules. So I have three rules which mimics the structure that I have on monads. One rule that says that I can relate two returned values at some specification that I'm for the moment calling return, and which depends on the two values. I can always weaken a specification when W entails W prime. And I can bind, if I have two computations that bind a first computation and then a continuation, I can provide a specification, which is a composition of the specification for the subprograms. So now let's have a look at an example to see what this return and bind object, that relational specification that I just gave you can look like. So if we take the specific case of predicate transformer for state, we may want to consider such an object of relational specification. It takes as input a post relation on final values and final states, and it returns a pre-relation on initial state. And then, so you can see that this object of relational specification takes two types as input, the return value type for each of my programs, and returns a type of relational specification. Moreover, it comes equipped with operations, return and bind, inherited, in some sense, from the structure of the continuation monad to prop that we can recognize here. And moreover, this object of relational specification is also equipped with an order which comes from the entailment order on proposition. And finally, looking at this operation, we can realize that this is exactly the structure of a relative monad in the sense of alternate Kirchhoff rule, meaning that even if it's not, strictly speaking, a monad which would need to take a type and return a type, it is a monad relatively to the product functor that takes two types and put them together as their product. In a similar way, we have the way to explain computation as relational specification is a function that takes two computations, for example, here, two-state computation, and provide a predicate transformer to state in this particular case. And this relational effect observation that explains my monadic computations as relational specifications preserve both the return operation and the bind operation in the sense that they are mapped to the one of the relative monad structure that I have on my object of relational specification. And so it is a relative monad morphism over different Bayes functors, something that we had to define in our paper to extend the existing work in the literature. And we can provide such relational effect observation for various kinds of effects, non-determinism, I/O, probabilities, exception, and then reconstruct program logics out of this relational effect observation. So let's have a look once again at exceptions, because something interesting happens there. If I want to specify exceptions, I could take this object of relational specifications that maps post-condition on result values and an exception or an exceptional state to preconditions. However, having only one exceptional state means that whenever my two programs raise an exception, then I'm not able to say anything about what happens for the other program. So I would rather have something where I have two independent exceptional cases for each of the program. This is interesting. However, if we try to implement the bind operation to compose a specification of this type, we are stuck. In the case where my two programs return a value, I'm able to use a continuation that takes two return values. And in the case where I have exceptions, I'm able just to forward the exception. But in the mixed case where one program returns but not the other, I don't know what to do. So in order to resynchronize the program, I actually need to provide also unary specifications that allow to provide this synchronization on the side where the program didn't fail. And with this unary specification, we can define refined relational judgments, which carry not only the relational specification, which is at the border, but also the specific unary specification of each of my two programs. And then, in the same way as I did before on my simpler judgment, I can define generic monadic rules for such triples. And here I have a bind specification for the left program, for the right program, but also one for the whole relational specification that takes as input also the unary specification of each of my programs. So finally, the interesting point is that actually I can unify all these simple judgment and refined judgment under one categorical abstract framework, which is that of relative monad. Indeed, in the unary setting, a specification monad is just a relative monad over a discrete functor. In the relational setting, in the simple one, a relational specification monad is just a relative monad over a product. And in this more complex setting of exception, where I need to keep track of unary specification, my object of relational specification is just a relative monad over this functor that maps a pair of types to the total relation over these two types. So what did I present to you here? Well, a generic framework which applies to arbitrary monadic effects. And in the paper, we derive relational program logics for a variety of effects, such as exception, imperturbed non-determinism, discrete probabilities, and unbounded iteration. And now that this framework is there and actually implemented in Coq, you can derive your own relational program logics just by providing the ingredients that the framework asks for, meaning the input monads, the relative monad for relational specifications, and an effect observation between these. And the key ingredient to make all this work is the notion of lax relative monads and their morphism that we explain in more detail in the paper, as well as the small extension that we provide. So on this, I will finish, and I will be taking your question.
Question? Can your framework also handle these so-called asynchronous rules?
Asynchronous?
Rules.
Rules, yeah, of course.
How?
The idea is that for each operation that you want to interpret, so asynchronous rules will be for generic monadic things are just derived from the monadic equations that you have on your monads, meaning that you can derive them out of the rules that I gave you. For effect-specific rules, you need to choose exactly what you want, and there is some inventivity, let's say, to which rule, whether the rules need to be asynchronous or not. For example, for probabilities, providing just asynchronous rules is not the same as providing a synchronous sample rule.
Thanks very much for your talk. You mentioned a bunch of language features that you can handle, but I didn't see any mention of concurrency. Can you make a relational program logic for reasoning about concurrent programs?
We didn't try yet. You will need to provide first a monad for concurrency, I guess some kind of resumption monad, and then to think a lot about how you want to specify your relational specification, like how you want to encode the context in which your programs execute in some sense.
Any other questions? Is there? No. Just a second. Let me check. No, Slido. No. No more questions. Oh. Okay. So we have actually 3 minutes. So plenty of time for questions. Anyone?
This may be a naive question, but in the context of logical relations, you can sometimes construct a binary logical relation by taking a unary logical relation and using sort of the second program as a specification for the first program. So I was wondering if you can do something similar here. Like construct a relational program logic from a sort of unary program logic. Sorry.
So yeah, we can do that. It is in the paper. If you have a unary effect observation in some sense, you can so from a relational specification monad, you can always precompose like the product functor and obtain what we call a relative monad over a product. This is kind of abstract nonsense. And then in order to have an effect observation, there is just one condition, which is commutativity of the image of the two monads that you are interpreting. So if you have only one, you need to show that any two elements in the image of your interpretation commutes with any other. So we have, this is detailed in the paper.
Okay. Is there more questions? Okay. So I think it's a good time to switch. Okay, thank you to the speaker.